actually, it'd be more correct to say I was a leading authority in quantum gravity. I began in 1970, a long time ago, working in that subject. And I worked in it for about 30 odd years. But during that time, I became more and more concerned about certain very fundamental questions, which it seemed to me went way beyond any of the particular research programs at that time. And which really wanted to do with the foundations of quantum mechanics, particularly its mathematical foundations. And for that reason, in the sort of mid-1990s, as Bob says, I did start thinking about Topos theory. I came across Topos theory purely by accident. It's one of these wonderful things, you know, you wander into the maths library looking for something and you pick up the wrong thing, and lo and behold. And I started reading it, and I was first interested as the models for space and time. You see, for a long, long time, I've wondered, why is it we model, as physicists I mean, we model space and time with sets? Because sets of points, right, elements. But I mean, is there really such a thing as a point in space? You know, a point in time? I mean, if you ask any physicist that, they'll say, well, not really, you know, it's a sort of approximation. Well, okay, it's an approximation, but then what is it an approximation to? What's the reality? So I started reading locales, and mainly Steve Vickers' book, actually, and work at first, with the idea of thinking about models for space. But then I started right at the beginning, very elementary. I came across the theory of presheaves, and I got very excited because I suddenly thought maybe if we could use this in quantum theory. And that's what I've been doing ever since. So I gave out working on quantum gravity over 10 years ago now, so I'm no longer an expert in that subject. So in Jeremy Butterfield and I worked on this in the early parts of early 2000s, but then we got stuck at a certain point. Now you can't see this in the papers we wrote because they're skillfully written, but actually there was something very fundamental. I didn't really understand what we were doing, and neither did Jeremy, so we went on to something else for a while. And then quite by chance Andreas Doring and I met, and it transpired that what Andreas had been doing for his PhD in Frankfurt with a pure mathematician, it was like a dowry, really, when he started working. It was like the dowry the bride brought with him was this thing we've called Dasonization, which is absolutely fundamental to what we're doing. So what I'm going to do is to give you a fairly general talk to start off with about how is I anyway perceive, or conceive rather, the use of Topos theory in physics. Now it's not the only way, I hasten to add. This is not a review paper, talk rather, about Topos theory in general and its use in physics. I suppose I might try and do that, but it'll be something quite different. It's quite fun to say that already there's so many people working on this use of Topos theory in physics that it's not that easy to give a review talk. Right? It's not just Andreas and me, it's a few other people too. Okay, so and towards the end of this talk I'll get a bit more technical and explain how, some of the more recent ideas we're doing and how it all fits together, I hope. Right, so let's get started. I'm not used to doing this. I grew up with overheads, you know, and this sort of thing. But Imperial College, in its wisdom, to celebrate the 100th anniversary of our founding last year, gave me this present. I gave it to everybody, actually. It's not that good. And it's one of these things. And also, Andreas seduced me by introducing me to something called, was it Beamer? Yeah. So you can now produce what look like PowerPoint presentations with mathematics in. That's what I'm going to do. I'm not very good at it. It's not my natural lecturing style, right? Anyway, let me start off talking about quantum gravity. Now, everybody motivates everything these days with quantum gravity. Anything vaguely dubious. Well, put it this, anything interesting, any mathematician who finds something of interest and thinks it would be nice to use it in physics always says, aha, quantum gravity. Now, why do they do that? And why do we do it too? Well, there are good and bad reasons for that. The good reason is that actually the problem of quantum gravity is still a major issue in modern theoretical physics. There are certainly very many people who work in the subject, no doubt about that, particularly in string theory. But at the basic level, there's still certain fundamental questions, which most people agree are there, actually, which are worrying. They cross across with different approaches. That's why they're interesting, really. They kind of transcend any particular school. And it does raise deep problems of both mathematical and less philosophical kind. Let me start off general relativity. All right. We know in general relativity we have something called space-time, whatever it might be, which is represented mathematically by a differentiable manifold. That's the mathematics of it. So you've got good old set theory, you've got manifolds, you've got differentiable functions, the whole whack, right? Absolutely standard. And from the first philosophical point of view, in a sense, general relativity is the ultimate classical theory. It was the ultimate sort of apotheosis, really, of classical thinking, was general relativity. And in that sense, it's the ultimate realist theory. I mean, in general relativists really do talk about the gravitational field. Though, having said that, quite aside from anything to do with topoi or locales or anything else, for a long time it's been the case that the reality of space-time points is in fact very dubious. Many people would agree on this for a number of different reasons. One is a purely technical thing through GR. The GR is actually invariant. The formalism is invariant under, or covariant, depending on how you look at it, under this group of space-time diffeomorphisms. Now, since diffeomorphism moves points around, it's saying it's invariant under moving one point into another. So in a certain sense, it's saying that points have no physical meaning whatsoever. And there's a certain sense in classical general relativity where that's actually true. The notion of a space-time point is a point in the manifold, has no physical meaning at all. And that's correct. So that's one sort of cautious remark about points. Another one is something, again, that physicists have been saying for a long, long time, is the use of the real numbers to model where you are. I mean, Euclidean space, Minkowski space, time, general relativity, manifold, it's all the same thing. Use real numbers basically to say where you are. But now, a real number is a very abstract thing, actually. It's one thing counting, 1, 2, 3, 4, 5, rational, 3/4 and so on. But real numbers are a very abstract construction. If you go through the Cauchy sequence or Dedekind and cut construction, if you've done that sort of course as an undergraduate, it's not particularly obvious that you would use that to model things in physics. I mean, you know, it's not obvious. It's in some sense, people say it's an approximation. If you ask any of our undergraduates or experimental friends here, why do they use real numbers? They say, well, it's an approximation. I mean, can you say that something is root pi centimetres away from here? Well, not really. I mean, what does that possibly mean? It's an approximation. But to what? That's the question. So this, for a long time, this has been regarded as being somewhat dubious, the use of... wrong way around. I just illuminated my foot. So, abstract concept. Okay, that's general relativity. And then we have quantum theory. Now, quantum theory, one of the problems of quantum gravity is that quantum theory, as it's normally formulated, works within a given fixed space-time background. I mean, it's always of ordinary quantum theory. If you think about the lectures you went to as undergraduates, I mean, you take it for granted, you write down psi of x, that the x belongs to R3. I mean, that is the fixed space in which you're working. And then you have the t on Schrodinger's equation, that's a fixed t. So there's an external space-time. You go to quantum field theory, well, the same thing applies. You've got external Minkowski space-time, so it's fixed. And quantum theory really is about things done in space-time. And the reason for that, one of the main reasons is partly is actually the instrumentalist interpretation of quantum theory. We all know very well quantum theory does not in itself, in its normal way it's thought about, anyway, say you how things are. It tells you what would happen if you were to make measurements. Now, measurements are things that take place in space and time. You know, it takes a certain amount of time to make a measurement, and you have to do it somewhere. You can do it here, there. So space and time are presupposed. They're given and fixed. And so right at the very beginning, you can see from a very, very general perspective that if you try and bring together quantum theory and general relativity, there's a clash there, a conceptual framework. I mean, this is very well acknowledged, and people were saying this 40 years ago when I first started. In fact, what got me excited, actually, was this clash. Okay. Perhaps I should... You see, I really haven't got the hang of this at all. Okay. So let me come to the... oh, I've skipped. Sorry. It's very unprofessional, but... yeah, okay. So the final question then on this slide is how can you apply these things to space and time themselves? As I said, I mean, there's a apparent clash. Now then, at this point, anyone giving a talk on these things always looks at the audience very meaningfully and says Planck length. You see? Planck length. Now the Planck length is the length which you can just get it by, it happens if you take this combination of things that arise in physics. G is Newton's constant, that's gravity. H bar is Planck's constant, so that's quantum theory. And C is the speed of light, well, that's right. You take this particular ratio, take the square root, and lo and behold, you get some of their units of length. Now, this has mystified people for decades, but it's true. And if you turn it into seconds, it's no, because these are very tiny distances and very tiny seconds. But the wisdom, you see, at this stage, you say, well, something dramatic happens from the nature of space and time at these scales. This is a sort of dimensional analysis, which physicists are very fond of. Now, because we have no idea what that is, and therefore you can motivate anything, you see. So any research program, any grant you apply for in quantum gravity, you know, if you're up for promotion, been interviewed and so on, someone says, why are you doing this? You say, Planck length. Something mysterious happens, and people go, something mysterious happens. And in fact, it seems to be true. The question is, what is not so clear is what it is that actually happens. Now, if you look at the main, I mean, at the current stage, there are more than one main research program in quantum gravity. The biggest one by far numerically is string theory. The next biggest one in terms of number of people working on it, anyway, is loop quantum gravity. And there are other things too, which people work on, which I may touch on briefly later. These are two big ones. Now, in their own separate ways, and I won't go into detail, because they both negate the idea, roughly speaking, of gain of points in space and time. They both suggest an open space-time points is not really that fundamental. I mean, string theory obviously is dealing with loops in some way. Now you may say, hang on, it's loops in something, isn't it? Isn't a loop a collection of points? Well, the answer is yes at one level, but then they make the loop kind of a thing in itself and abstract it out in a way from the space in which it sits. That's the kind of way things go. So in some way, these are both suggesting that points don't make much sense. And the idea of dimensional analysis is if you were to get down to this incredibly tiny distance, you would find the notion of a point, baseline point just fizzles away for some reason. What is left, that's not, I think. In any event, all this suggests that what we need is a non-manifold model. I realise I tend to point at this thing because that's totally useless, isn't it? You see, bad habits. Oh. Oh, dear me. Yeah, I went to master's. I mean, everyone else in the college can use this damn thing. Oh. There we go. All right. Okay, let me move on, if I can, to the next slide. Got it. Okay. Now, what do we normally do in theoretical physics? I mean, well, we have what I call the unholy trinity, which is the collection of three things which physicists supposedly use in constructing theories of physics. One is the real world. I always feel a bit embarrassed about mentioning this, but there is actually supposedly something out there which the people at CERN spend vast billions of pounds on, called the real world. And then we have, that's the data, how things are as we see in the world. Then there's the mathematics we choose to use in constructing a theory, the type of mathematics. And then there's a conceptual framework, if you like, the philosophical framework, within which we seek both interpret and formulate the theory. And this triangle underpins all theoretical physics. Now, the trouble in quantum gravity is that the first one is very largely missing. Although there have been, oops, it's the wrong button, that's the problem. Okay. This one, real-world data, although there have been some interesting discussions about this in recent times, is by and large missing. So all we have is mathematics and conceptual framework. Now, that's a very strange way, if you think about it, to develop a theory. Because what has happened over the years in quantum gravity, people said, there's general relativity, there's quantity, they don't fit. What can we do? And they just invent something, you see, broadly speaking, which is something to do with general relativity, something to do with quantum theory, and they call that quantum gravity. And this is very strange because it means that no one really knows what they're looking for. I've often wondered this, actually. If you just woke up one day and you found a big pile of papers on your desk, and somehow you got this mystical message, this was a quantum theory of gravity, would you know whether it was correct or not? It's not so obvious that you would. I mean, if someone wrote a theory which unified all the elementary particles, explained the relations, went beyond the standard model, fixed all those unspecified 20-odd constants, you'd know at once what it was they'd done. But quantum gravity is not so strong in what you're looking for. That's part of the trouble. Which is interesting, actually. I can just divert for a moment as to, because I'm rather intrigued with this, I've always been intrigued by this. What makes any particular idea a good one? Now, no, this is interesting. It's not a joke. It's an interesting question. I mean, these days I'm one of the college deans, which is very fun, actually, because I get more research time since I was a student. It's a good job, not a bad job, as you might think. But it's good fun being a dean. And deans, apart from anything else, they have to be a dean on every interview committee or any appointment, you see, so interview lots of people. Now, if you get someone in front of you who purports to work in quantum gravity, you see, and they say that I've done this, that, and the other, how do you judge whether it's good or bad? Because you can't say because it fits the data. I mean, people pretend it does, but that's, that's a game they play. We all know that. It doesn't really. I mean, what do you say? Okay. The same thing applies to research grants. Now, I often wondered the same thing about pure mathematics. And some years ago, I was sitting next to Michael Atiyah at a dinner for some reason, and I said to him, how is it your profession decides what is good mathematics, you see? He looked at me slightly haughtily. He said, it's what the good mathematicians choose to do. Which I thought was a slightly circular argument. It's something it's like music, you see. If a composer writes a nice tune, or pop music, I mean, why do people like it, you see? They do. And for a while everybody sings it and it gets cites, they buy it, journal of citations, and it goes away. Now, I've been working in quantum gravity for so long now, I actually can see cycles of this happening. For a while people are totally excited by something, they all cite each other, and it becomes the thing of the moment, and it dies away. Now, if you're lucky, if you're a young person, if you're lucky, you're working on something which at the moment you can't be interviewed by a dean, is thought to be, it's in a sort of delta function peak of activity. But it is curious. I was once, do you know the Potsdam Institute in Germany for general relativity studies? It's a very big Max Planck Institute. And when it was thinking of setting it up, I was invited with other people to go there and give a lecture to the committee who were going to award the money, you see, whether it was worth it or not. And I was asked to give a talk on quantum gravity. So being an honest sort of chap, I stood up. I more or less started off by saying this. I said, really speaking, I said, quantum gravity is not a branch of science at all. In the way that Popper would recognise it, you can't falsify anything. It's not a branch of science. And my host looked absolutely horrified. Anyway, he gave the money anyway. So, but it is true. So what do people do? Well, all our work is on my analogy with other theories, quantum field theory, quantum chromodynamics, anything we happen to know. I mean, you take that and you gauge theory, you start from there, you see. And the other thing is people simply indulge in personal mathematical interests and philosophical prejudices. And to be honest, you see, if all you've got is those two, what else do you do? I mean, Paul Davies once accused me, he said each year I walked into the maths library, closed my eyes, pulled a book off the shelf, and that became the maths I used for the next year, that's what he said, which was slightly unkind. But anyway, I could say a lot about this, but I won't. But it is just a curious fact about research in this area, is that it's not like ordinary science. And sometimes it's worth remembering that, because we are supposed to be doing physics. We shouldn't forget that. I mean, obviously, if you're interested in maths, that's fine, but pure maths, but we are doing physics. I've lost it again. Okay, so let me come to what I regard as one of the main questions that I really want to address, which is this. What is the status of ordinary quantum theory when applied in quantum gravity? This is the thing that's worried me, as I've said, for a long time, is that certainly all of the big insensitive people working on standard research programs in quantum gravity do presuppose ordinary, absolutely bog standard quantum theory. Now, okay, in the one sense this is understandable, because what else can they do? It's what you've got. But nonetheless, it is, I think, extremely suspect. There's two particular issues that have been at least partly motivation for what I've been doing with Andreas. One is the a priori use of real numbers. If you think about it, all of the standard formulations of quantum theory, whether it's Hilbert spaces, C-star algebras, deformation quantization, geometric quantization, quantum logic, path integrals, whatever you want, all of them more or less presuppose standard use of C and R, complex and real numbers. And that's one issue I find very, very problematic, actually, that right at the very beginning, in trying to formulate a theory of quantum gravity, you presuppose the existence of things like real numbers and continuum. And that seems to me very, very dubious. And the second thing, which is a very old and much debated problem, it's an interpretational one, is that quantum theory, as normally understood, is an instrumentalist theory about what would happen if you were to make measurements, whereas as far as space and time are concerned, we particularly want the way things are. We like to think of space and time as actually being there. And what could it really mean to make a measurement on space or a measurement on time? I mean, how long would it take to make a measurement on time? I mean, it's kind of you might measure time looking at your watch, but that's not what I mean. It's a curious concept. Some Roger Penrose, who's thought a lot about these things, I mean, believes that fundamentally there's some sort of super selection structure so that space and time themselves always remain classical. That was a mistake. I've just lost the... Come on, Andreas, you know this system. I pushed on I shouldn't have done. I've lost the picture. Okay, I'll reboot unless we're careful. That's
what is the problem?
Well, it was big, now it's small.
Okay.
Yeah.
Just press on the small picture once again.
As a man who knows. Thank you. It's simple when you know. Yeah. Okay, so we have these two problems. Now, let me come to the role of real numbers in physics. I mean, how do we actually use real numbers in physics? Now, there's different ways you could probably look at this and say this, but it seems to me that there are at least three different ways in which we use them. The first is the values of physical quantities. We assume energy, momentum, position, all the things we talk about are real numbers. Right? We take that, in appropriate units, of course, we take that for granted. It's the first thing. The second thing is that they arise in quantum theory or classical physics as values of probabilities. Probabilities lie between 0 and 1. They're part of the continuum of numbers. We assume that automatically. And the third one, of course, which I've mentioned already, is that they are a fundamental ingredient in our models of space and time. In the case of GR, values of general differential geometry. In the case of classical physics, it's just, ordinary physics, it's just Newtonian Euclidean space and so on. Now, I would claim that the use of the real numbers and a priori, a fortiori, the complex numbers in standard quantum theory is actually a reflection of these two and indirectly of this as well. And that's the problem, I think, anyway. Let me come back to this first question. Why are physical quantities assumed to be real valued? I mean, it may seem a silly question to ask, but actually, why do you suppose that the energy of something, say classic, is a real number, like root pi joules or something, you see? Why do you suppose that even makes any sense at all? Now, I think the reason for this is certainly, traditionally, I hate to mention rulers and pointers, they make me sound really antiquated, but broadly speaking, you measure things, right? You're used to measuring things in physics. You measure them with how long something is or how fast something is moving. Or I mean, you measure things in space and time. And I think if you think about it, you can see there's a direct link between the quantity value space, as I call it, that's the space in which things take their values, real quantities of quantities, and the assumed structure of physical space. So the reason why we assume physical quantities are real valued is because we assume a priori that physical space is modeled with real numbers. And in the case of quantum mechanics, this is clearly what you're doing, because if quantum mechanics are particle moving in the same three dimensions, you have operators x and p, and the whole formula is set up so they have continuous spectra. Right? Why do you want x to have a continuous spectra? Because that's what you think space is. Right? So you've built into quantum mechanics right from the very beginning, into wave mechanics, the real numbers, the complex numbers, because you want to get them back again as the possible positions of a particle. But that is assuming something about the structure of space. But supposing space is not like that, what then? Then it seems to me the whole thing is absolutely wildly, it's what the philosophers call a category error, is that you're using in one domain of experience ideas drawn from another with no actual logical link between them. And the more I think about this, the more I'm convinced this is true. You make a very, very serious error in quantum gravity if we start off with a formalism which uses real and complex numbers. And yet that's what they all do, with one or two honourable exceptions. But most formulas, certainly all the big ones do that. But then, of course, the question arises, well, if the quantity value space is not real numbers, then, I mean, what happens to the Hilbert space formalism? Because it's very rigid. You know, it's very hard to change quantum mechanics. So I'll miss that one. It's come to the big problem. So the big problem then is this, as I see it. The standard quantum theory, in its essence of its formulation, is grounded in ideas of Newtonian space and time. Or if you want special relativity, that's a very minor and irrelevant modification. Right. Now, as I say, I think that's a category error. Right. So the question is, what do you do about it? So how can you modify the formalism or generalize it so as to be, if possible, realist? Because in inverted commas, this is important what we're doing, but in some sense realist, so you can talk about space and time as if they were vaguely there. But also not to be dependent a priori on real and complex numbers. Now here, for example, is an example I'm particularly fond of. I mean, now we have Faye Dowker, who works on causal sets. Now, causal sets are interesting things because they're discrete. They're discrete models for space-time, which are basically partially ordered sets. So this sort of thing, and the ordering is kind of sort of a causal flow of things. So these things are meant to model, in some sense, space-time points, or at least points where events can take place. And then these arrows indicate the causal links between them. Now, supposing for some reason we suddenly knew that there was such a thing as the causal set of space-time, then if that's what we have in place of Newtonian space and time, or special relativity, what would be the appropriate type of quantum theory for that background space? Right? Suppose I have started from scratch. I can't use real and complex numbers. I have to go back to the idea of making measurements, values of physical quantities. The values of physical quantities have to be determined in terms of the structure of this thing. Just as in ordinary quantum physics, we determine the values of physical quantity in terms of the given Newtonian space. Now, this is a huge question to ask, and it's a totally fascinating question. Now, at this stage, I have no idea what the answer is, but it's an enormous and, I think, very intriguing challenge, and certainly one of the motivations for what we're doing is this type of question. It's very difficult to answer it because the Hilbert space formulation is very, very rigid. Now, of course, this raises the general question then, well, what actually are the physical principles of quantum mechanics? I mean, if you say we want to get beyond quantum theory, what is it we're going to keep? Now, as I've said, Andreas has perverted me to the use of this beamer thing. Now, think about beamer. This looks like a PowerPoint presentation. See? Now, there's a dean one of the things I get to sit through is endless PowerPoint presentations. It's something about a rector saying what a wonderful place Imperial College is, but usually it's by people wanting to get jobs, saying how wonderful they are. And particularly the medical faculty, they're absolutely fantastic. I mean, their presentations, they're works of art. They really are. I mean, pictures and all sorts of lovely pictures and diagrams and fascinating things and quotes from various people, you see. Now, I can't, of course, reproduce that. Neither have I slightest desire to do so, actually. However, I can't resist having a quote, because you always have quotes in PowerPoint presentations. Now, I've learnt that as being. Now, here's the quote from Heidegger. Heidegger thought about this. I mean, I'm interested. I'm very actually interested in Heidegger's philosophers. It happens anyway. But he has a particularly interesting book called "What is a Thing?" And that is a fundamental question. That's what we're talking about. What we're actually talking about today, at least I'm talking about, is what is a thing? What do you mean by that? And here's Heidegger's question. He has a book called that. This comes right early on. He says, from the range of the basic questions of metaphysics, we should here ask this one question: what is a thing? The question is quite old. Well, that's true. Plato whined about it in the Pre-Socratics. He says, what Irene ever knew about it, merely that it must be asked again and again. That is absolutely right. The whole history of physics is about people asking the question, what is a thing? I'm asking the question today, and today I'm going to give you a Topos answer to what is a thing. That's what I'm asking. Maybe wrong, of course, but nonetheless. Now, here's Heidegger's answer to his own question, which you find about page 60 of the book. This is very, very interesting, because a thing is always something that has such and such properties. Always something that is constituted in such and such a way. So this something is the bearer of the properties. The something, as it were, that underlies the qualities. So his concept of a thing is something. If you ask what word something means, you have to forget that. So for Heidegger, a thing is something which somehow bears properties. So for him, a thing actually says is a bundle of properties. Now, property is the way things are. So for physicists, the property will be the energy is equal to this, position of the particle is equal to that. So that's for Heidegger. He says that's what a thing is. It's nothing but that. Right? Now, that's interesting, because that's precisely the classical view of what a thing is in classical physics. He's absolutely spot on, and it's exactly what goes wrong in quantum mechanics. I'll come to that in a second, but for the moment, let me just aside, almost as an aside, say that as far as constructing theories of physics is concerned in general, what we need to do are to get mathematical models for three things, really. One is the space-time and space-time we can talk about. But the second is physical quantities, as I've said already. And the third is the notion of states of a system. Now, the state of a system, a state is roughly something which specifies the way things are. It can be a history version. It doesn't have to be at a given moment in time, but that's roughly what it is. So here are the key questions you'd have to ask in those circumstances. I mean, what do you mean by the value of a physical quantity? I come back to that question again. What do you really mean by it? How is this related to the idea of a property? Because normally a property is the statement that something has a certain value. And of course, how does the state determine the properties of the system? These are the fundamental questions that physicists always ask for any theory of physics. If you look back through the whole history of physics, at least post-Newton, you'll find these essentially the questions that are being asked. Now, let me now introduce a bit more mathematics and turn to classical physics and show how in classical physics Heidegger's perception is totally realized. So in classical physics, what do we do? Well, we have something called a space of states, which is this calligraphic S at the top there. Ooh, that one, which is a symplectic manifold, if you want to go into it. And the physical quantity A is represented by a real-valued function S. And the interpretation of that is that a state S, little s, determines the way things are, say at a given moment in time, and then the value of the physical quantity in that state is a real number. So for any state A, you can find out the value of a physical quantity by working out what A of S is. And that's how it works. So every physical quantity has one of these functions, and therefore for any given state, you can predict or say specifically what is the value of everything. All right? And that's naive realism, if you like. In particular, that means that everything has properties. Because if you take a subset delta of the real line, this thing, then when a basic physical proposition is A belongs to delta, that's saying the value of the physical quantity A belongs to that subset delta, you see. And that's a proposition about the system. I mean, delta could be a singleton, right? But it's a proposition about the system. How do we represent that? Well, it's simply A to the minus 1 of delta. It's all those sets in S, or sorry, it's points in S, which the proposition is true. So in other words, this represents a subset of S. Now, this is fundamentally important. I can never say this too often. But in the way that classical physics is set up, the mathematics that you choose of necessity, propositions, or properties if you like, are represented by subsets of a set. And then the mathematics comes in, because of course you know very well the collection of all subsets of a set is a Boolean algebra, and therefore of necessity a priori, in classical physics you always talk about the logic of Boolean logic, talk about physical properties. So Heidegger could have added, and he wouldn't have thought about doing it, and by the way, you have to use Boolean logic. But that's exactly what you have to do, and you can't get out of it. There's no, as long as you think yourself realist in this way, that things have values, then you get that. It's very, very important. And also, of course, these propositions form the deductive system. So you can argue about the system using these propositions. And that's how classical physics works. Now, the great kerfuffle at the 1920s was the fact that it doesn't work in quantum mechanics. And there's this famous theorem, the Koppen-Specker theorem, which says that you simply can't do this in quantum theory. It's impossible to assign consistent true-false values to all propositions in quantum theory. In other words, you cannot talk about properties of things, as Heidegger wanted to, in quantum theory. Heidegger's definition is wrong. A thing, in quantum mechanics, is not a bearer of properties. Not all properties, anyway. It's not. It doesn't work. And the chaos theorem tells you that. I think this theorem is so important, I think the physics undergraduates should be told this on their first day here. I've done it again. When they're being told where the bar is and where the library is, they should also be told the Koppen-Specker theorem, so I can never forget it. It's so important. So it says that it's impossible to consistently assign values to all physical quantities in quantum theory. So from Heidegger's perspective, there is no way things are. If someone had told Heidegger this, he said, well, that's terrible. Then the world doesn't really exist. I mean, there are no things. What he would have said, there are no things. And of course, that's in a sense is what classical quantum mechanics said, because instead of talking about things as things actually being there, they adopted instrumentalism, talk about measurements. It's told what would happen if you made measurements. If you made measurements within a given space-time background. This is why you get this horrible clash in quantum gravity, right? But you get driven this way. You have no option by the mathematics. Now, here we get to beginnings of Topos ideas, because let's step back for a moment and take stock again of what I've said about how we represent physical quantities and things in physics in general as theoretical physicists. So we start off again with classical physics, right? So we look at these propositions, A belongs to delta. Classical physics, simple. You have a state space, symmetric manifold, as I said already. A is represented by a function, called C smooth function from S to R, and then these propositions belong to subsets of S. They form Boolean lattice, right? That's classical physics. What happens in quantum mechanics? It's totally different. In quantum mechanics, state space is a Hilbert space, pure states anyway. Physical quantity gets represented by a self-referent operator, and the thing that represents the proposition A belongs to delta is in fact the spectral projector. It's the thing that it's the projection operator onto the spectra, or onto the eigenstates, if you like, of the operator that lie in delta. So it's a projection operator, and of course it's infamously famous that several projection operators is a non-distributive lattice. It's not something you can. It's not a logical thing. You can't reason with it. Right? It's not much use for logical purposes. That's quantum theory. So that's where quantum theory differs from classical physics. Because one of the things that strikes you about this is that, by goodness, they look totally different. And when you first teach quantum mechanics or learn it as an undergraduate, the first thing you're struck by is how completely alien quantum mechanics is if you haven't seen it before. I mean, when I first encountered it, I was absolutely poleaxed, I remember. When I first started lecturing to students, I always found there were some students who just didn't believe me. They'd say, no, you must be wrong. I said, well, look, I'm a famous man. I wasn't actually, but, you know, I said. And they said, no, you must be wrong, see. Because they were Heideggerians, you see. They were so convinced the world existed, but they didn't believe me. Well, maybe they were right, I'm no nearer, but I was telling them the established wisdom. Okay. Now, isn't it curious that these things look so different? Wouldn't it be nice if they both looked like two different examples of the same thing? Now, how could that possibly happen? Well, because there's the possibility that arises in abstraction. Now, you're here because you're interested in category theory. I don't need to defend this to you. If I was giving a lecture to the physics department here, it would be a pretty tough point at this stage because they'd all walk out. But you all know anyway that category theory is a fascinating subject. So I'll simply tell you what our suggestions are. I mean, Andreas and I, what we're trying to do is to say, well, let's take the classical picture for a moment. Whoops, wrong one. That one. And let's generalize it, just to see what happens. Let us suppose that rather than doing this, this, and this, we instead say, well, let's say that we have two objects in some category Tor called sigma and r, And sigma is the analog of the classical state space, and R is the analog of the real numbers in the sense of the space in which things take their values. And then a physical quantity is represented by an arrow from sigma to R. Now, that's certainly true in classical physics. On the face of it, it's totally not true in quantum mechanics, but bear with me. So let's try and do that. And then also, let's suppose that for any subobject of R, there's a proposition, A belongs to delta, whatever that means. Right? It's a proposition about the physical world, which is represented by, hopefully, a subobject of sigma, just as here, it's a subset of there. Is this possible? Would it make any sense? Now, to use this at all as a physicist, you would certainly need some sort of logical structure on the subobjects of sigma. Otherwise, it wouldn't make any sense. Your proposition is not represented by something that's vaguely logical. You can't reason with it, so it's no good. Right. Now, is it true that in the general category, it works? The answer is no, it doesn't, because in general, the subobjects do not form a logic. This categorification, as I call it, it's always nice to invent words. So to categorify a theory is to write in category form. Does it work? Well, not always, because not in general. Subobjects do not have logical structure. But of course, they do in the topos. Right. Now, I'm assuming most people here know what some of the topos is. For the benefit of those of you who may not, I'll simply say that it's a category which behaves very much like set. That's the critical point. A topos behaves like set theory in some of the most critical ways that are important for theoretical physics. That's why I think it's so important for physics. The way in which topos theory looks like set theory is exactly what you need to use it in the theory of physics. That's what's rather striking. Because when you first read about topos theory, you don't understand that. I mean, physicists don't understand that. So anyway, you have initial objects, terminal objects, pull-outs, all that sort of stuff. What is important really for us is this thing. And I'll draw a picture about this because it's sufficiently important. It's worth emphasising that in set theory, if you have a set B and a set A is a subset of B, you have this characteristic function, chi of A, which is a function from here into 0, 1, which you think of as false and true. And this is defined on the whole of B. And any particular little point, little x in B, if it belongs to A, you say chi of A is 1. If it doesn't, it's 0. Right? Everybody knows that, of course. It's the characteristic function of A. And that determines A. Now, what is absolutely fundamental in topos theory is that the same thing is true. There's something called the subobject classifier, which is the analogue of, will be for us, the analogue of true or false, when interpreted physically, with the property that essentially the same thing applies, the same diagram applies, that you've got an omega there, rather than 0 and 1. So this thing, in some sense, this object in the topos, the object in the category, is what is the analogue of the object 0, 1 in set theory, which is the thing you use to talk about things being true or false. Now, of course, that's true in mathematics, it's also true physically. One of the fascinating things is always to see how mathematical ideas get coded into physics. Actually. And it's interesting, particularly in this particular context, as I'll explain shortly. Now, as I've said, the thing about a topos is that you do have this logical structure. Now, again, everybody here will know that, of course, that you have there's two things. First of all, the subobjects of an object A, of course, form a Heyting algebra. And Heyting algebra is almost a Boolean algebra, not quite. Good enough for physics use, anyway. And the same thing applies to the global elements of omega. So the point in omega, and there are some points in omega, they do form a Heyting algebra. Now, Heyting algebra is distributive lattice. That's what's important from the physics point of view. It's distributive. So it looks like classical logic in that sense, but not quite. The only difference is, as you know very well, you don't have excluded middle. So, but it turned, well, you know this very well, most of you, that it doesn't matter. All that means is that you have to prove theorems constructively. You cannot prove theorems by contradiction. Because many mathematicians hate that anyway. If you want to prove something exists, to say, well, supposing it doesn't exist, and you get a contradiction, therefore it must exist, it's basically a bit uneasy. You think, well, wouldn't it be nice if you actually could show it exists? Well, when you're working inside a topos, you have to do that. But apart from that, you work just as normally. And certainly as far as physics is concerned, as far as I can see, there's no reason whatsoever why you shouldn't use this type of logic. It's intuitionistic logic. I mean, it's perfectly usable as a tool. Okay, so that's why the whole business makes sense, is the subobjects of any object do form a Heyting algebra. In particular, if we have this sort of state object, sigma, a special object, the subobjects which can represent propositions will form a logical structure, and that's why everything starts to make sense. And so we come to what you might call the mathematics of neorealism. Now, one has to be very careful here. We have a difference between maths and physics. Right? Proposition in physics is something about the physical world, whatever it might mean, right? It's about the way things are out there. A proposition in mathematics is about the way things are in there, or in your heart, or wherever you think mathematics lies, I don't know, or up in the Platonic heavens. Anyway, it's not actually out there on this table. Well, maybe it is, but that's a subtle discussion point. Anyway, you know what I mean. So, if you look at theoretical physics very carefully, what you spend a lot of your time doing, you start off with things in mathematics, and you carefully make an interpretation of them in physical terms. And it's very important, actually, to keep those two things separate in this particular case. Let me start off again with propositions in maths for a moment, and let's go back to set theory. So again, let's suppose you have a subset K of a set X. Here we are. So here's X, here's K. Then the proposition X belongs to K. Well, it's either true or false. Right? I remember once taking part in a theological discussion. One of my side interests is science and religion, with the then Bishop of Birmingham, you see, Bishop, a big man. And someone in the audience said to him, well, what happens after death, you see? He said, well, you're dead, you're dead. I mean, you're dead, you're dead. You're either dead or you're alive, you see. None of this heavenly stuff, just you're dead or alive, right? He was a Boolean man, in other words. He hadn't heard of Topos theory. So here's D for death, you see. So either you're dead or you're not dead, right? You lot, me, are by and large a moment outside here. Who knows? Anyway, there we are. Okay, right. And we could capture that in this, what you might call, oh dear, sorry, this valuation thing, which the value of this proposition, mathematically, is 1 if it belongs to K, not otherwise. In other words, this proposition is true if only if X belongs to K. Now you might think, boy, that's absolutely tautological, but nonetheless, it's true. Right, now what happens in a topos? Well, here you get this fascinating thing that the proposition can only be partly true. Because when I read this, I thought, my goodness, quantum theory. Because in a sense, in quantum theory, when you have superpositions of states, in a way, if you say the spin is up or spin is down, neither's true. But neither is absolutely false. You know, if you've got somewhere in between, sort of superposition, you can't say that spin up is true, but you can't say it's false either, because that probability is 0. So it's sort of in between, maybe. And somehow these Topos ideas seem absolutely tailor-made, because precisely they have this notion of partial truth. Now, the way this works is very simple to say. If you have an object in the Topos, say X, and so it does have a global element, little x, yeah. So some global element, then you have this proposition, new X belongs to K. It's just a composition of this. And in fact, it's just this. The main point is that here you have this term in object 1, which is just the analogue of a star, really. And the truth value, the statement that this point belongs to that, is just the combination of these two things. And that's absolutely fundamentally important, because that's, in a sense, the only way truth values come into Topos theory as far as physics is concerned. So any use of truth values in physics, however you do it, Topos values, you're going to have to go back to this bit of mathematics somewhere along the line. Right? And it belongs to the global elements of omega. So the global elements of omega are going to be what, as physicists, we would say are the values of physical propositions. Right? That's what's going to happen. And our claim is that if you do this, you can think of this as a certain type of, we call it neo-realism, because it's not exactly realist. In a sense, things aren't just true or false. You're not either dead or you're not dead. You're in these sort of in-between states, which seems to me fits quantum mechanics very well, actually. Anyway, there we are. Now, wrong way. Here's our main contention. By us, I mean, in case there's any something thrown at the fans, I draw Andreas into the discussion at this point. We're both to blame for this. Our main contention is this, is that you can profit somewhat anyway in theoretical physics if you consider the following generalization of what we normally do. For each system, each given theory type, by theory type I mean classical physics or quantum physics or D-physics. D-physics is Dorian physics, you see, the next generation's contributions to D-physics. Yeah, whatever. For each system S, which a theory is applicable, you can formulate it and interpret it realistically in a particular topos. So the claim would be, for example, take a point particle moving in 3 dimensions. That was a topos which you would use for classical physics, another topos you would use for quantum physics, and a third topos you would use for D-physics, or E-physics, or F-physics, or whatever. That's our claim. Of course, it certainly makes sense if you can rewrite quantum mechanics in this way, and you can. That's the whole point of giving the lecture, really. But that's the claim. When different theory types have different top-way representations. So set theory, you have a certain representation of the system. Classical physics, you always represent things in sets, but then in quantum mechanics, you represent it in a different topos and so on. So that's the idea, and then within that structure, we would say that we have in any given representation of this type two special objects, these sigma and r, which are the analogue of the state object in classical physics, and the real value is thought of as the values of physical quantities. These two objects. And then any physical quantity is represented by an arrow from here to here. That's the claim. Which, of course, is obviously true in classical physics. And then the second claim is that propositions about S are represented by subobjects of sigma, and these form a Heyting algebra. So that's the logic you have to use of propositions about the system. But like I said, it's perfectly usable from a physics point of view. In fact, many physicists have argued over the years anyway you should use constructive proofs, you never use indirect proofs like this. And then the third thing is that there's something, the analogue of a state is something called a truth, what we call what Jeremy and I in our original paper called truth objects, but we're now calling pseudo states because it's more clear. But there's an analogue of a state in toposes, in topoi, which will give you the truth values for things. You have to specify them, but they're just a bit more subtle than you think. That's the claim. And then propositions themselves are always going to be assigned truth values in this. That's the claim. Now, it'll be a complete idiot who would say that every theory you're interested in can be written in this way because someone will immediately find one that can't. All we're saying at this stage is that we're proposing is a very general toolkit for constructing new types of theory, which certainly go well beyond any standard ones. I mean, well, I'll come back to that later, but there's no question about that. You could invent new types of theory you simply wouldn't have thought of, I don't think, using the more sort of traditional ways of thinking. What's on around? Okay. So theory expressed in this way, it looks like classical physics, except classical physics always employs the topos of sets, whereas other more subtler theories, including quantum theory, and we assume quantum gravity, use a different topos. And if you want, although I've been talking about sigma and r, you of course can also include space-time objects if you wish in the theory. This is an interesting point to discuss whether you actually should do that or not, but you certainly can, in which case ideas of synthetic differential geometry would naturally come to mind. So if you wanted to do that, you could include that sort of way of thinking about things in this framework. So that's the idea. Now, of course, the interesting thing, as the experts will know, is that topos can be used as the foundations of mathematics itself. When I first read this, I was absolutely shaken, because I've always been a Platonist at heart, actually. I've always believed there's a universal, transcendental, beautiful world out there, lots of lovely people in it, and lots of grant money, and, you know, everything you would want, lots of postdocs, and things, you know, no rectors, that sort of thing. Lovely place, where mathematical things exist. And I thought that, you know, well, set theory is this sort of universe that's out there. When I discovered these things called topoi, and each topos could be used as a foundation for mathematics itself, I was absolutely shaken to the core, because I thought, well, it's like Plato had this problem. Can you have a form for each individual thing? I mean, if you start suggesting that, it gets ridiculous. So I still feel a bit psychologically weak on this point. So anyway, it is true, as you experts know very well, that topos can be used as a foundation for maths. And in fact, any topos has an internal language, which is very similar to the formal language that you use in set theory. Now, our claim is that if you interpret it in the theory, which is written in this way, you would use the internal language of the topos to interpret the theory physically, right? Because topoi are fascinating because you always have these two perspectives, the external and the internal. It's absolutely fascinating as to how they fit together. I could give hours of lectures on this now about what I think this means physically, and there's not time because Chris wants to start in 10 minutes, I know that. But it is a fundamental feature of all topoi, they have this structure. And so, whoops. Now, let me say just very briefly what we mean by a truth object. I shall need to be speedy about this because I'm actually running out of time, but let me come back to ordinary set theory for a moment. In set theory, basic mathematical propositions are of this sort. Oops. Oh dear. X belongs to K, as I said already. Or equivalently, that is a subset of K. Now, in classical set theory, of course, they're equivalent. They're not the same thing at all in topoi. And this turns out to be very important, actually, in the concept of a pseudo-state in physics. Because pseudo-states, it turns out, are associated with these things. In quantum mechanics, the object that you construct in quantum theory represents the states, has no points at all. Right? That's the Costa-Cochrane-Becker theorem. Nonetheless, there is an analogue of that statement, which is later called truth objects. Now, the way that maths and physics interlock is this. This is the mathematical statement that X belongs to K. This is the physical statement that the value of A belongs to delta. Now, the truth value of this that's viewed physically in the space S is 1 if A of S belongs to delta, where A is a thing that represents physical quantity, not otherwise. Now, this is a mathematical statement. Right? This is mathematics. This is meant to be physics. So the statement that the physical quantity belongs to delta in the state S, physics, is 1 if mathematically that is true. Now, that may seem incredibly pedantic to insist on that, but in fact, it's very important to realise that when you come on to look at these more subtle topos cases. Now, the trouble is, in a topos, the state object may have no global elements at all. It's the one thing that less is. In fact, there's the case in quantum mechanics. What's the analogue of a state in a general topos? These are things that we called truth objects. I say we, I mean sort of Jeremy and I called them some years ago now when we first looked at this stuff. Now, the basic idea here is actually quite simple. And maybe rather than going through these overheads, I'll just, well, let me just make this definition first. Let me define for a given, in classical physics, a given microstate S, let me define something called TS, which is this. Now, TS is simply the supersets of S. Viewed physically, it's all those propositions which are true if the state is S. Okay. Now, it's easy to see that if you think about it mathematically, if I call for a moment this A to the minus 1 delta K, that the proposition, say, S belongs to K, which is some subset, is the same thing. It's equivalent to saying that K belongs to TS. Those mathematically, those statements are identical. It's tautologically obvious, right? S belongs to K, and K belongs to TS. At the same time, that's equivalent to saying that this S is a subset of K. Now, what happens in a general topos, it transpires, I'll skip the details so as not to... yeah, I should stop for 5 minutes, yes? Very good. When I was younger, we were expert in quantum gravity, as you kindly put it, I was often had to chair sessions in which Roger Penrose spoke. When I was very young then, he was very senior, it was a nightmare, he never stopped. He just went on. In big conference, everyone's lining up to speak, went on and on and on, you couldn't stop him.
That's what Bob is doing now.
It doesn't help, make a difference. Okay, I will try and stop roughly in time. Now, what we do in a general topos is that you generalize things, but in a general topos, there aren't any little s's. So instead you have to construct this, and that does exist. You see, let me emphasize this again. The only propositions you have available in mathematics, really, are the form that something belongs to something. Little x belongs to k, right? Or if you want, this is a subset of that. And that's all you've got. And all your physical propositions have to be rewritten in that form. Now, this is not available to you in the general topos, but this is. And it turns out so is this. And in fact, I'll just briefly flash up the transparency that shows you because how these things are related. Is that in a general topos, you have a truth object. It's a subobject of this. It's a collection of subobjects, you see. It's like it was classically, just of subobjects. And then this thing has a k belongs to this. K represents a proposition in the topos. That has a truth value because that's what happens in topos. Mathematics, you see, it makes sense. The second version, the truth object, is to say simply a subobject of sigma. Now that's like this is, you see, here, this state is now thought of as a subset of sigma rather than a point in sigma. Right? Trivial difference you might think, but it's not actually. So you have the second version of a truth object is in fact a subobject. And then what you're looking at is this proposition. So the analogue of this, which you could have used perfectly well in classical physics, in classical set theory, you now, if you want to, can use this. Now you think, are these two related? The answer is yes, one-to-one link between them. In the case, if you start off with the T, which is where we started off in our original papers, you just take the collection of all subobjects, take the and of all of them, and lo and behold, you get this thing, which is the topos analogue of a single point. And that's just as good. So these things we call pseudo-states. And they're, in some sense, the closest you can get to states. Now, how does all this work in quantum theory? Well, I'm going to have to skip the language pretty. Let me say very, very brief. What we actually do, we've decided what we're doing, is that we're representing physical systems with a formal language. That's what we're actually doing. Each physical system has a formal language called L of S. And then different theories are translations of this into the internal language of different topoi. So you can think in terms of translations of languages. That's what physics is. Physics is a translation of languages. So in particular, there's a translation into, say, sets for classical physics. There's translations into different topoi for quantum physics, like that. Is that arrow from there to there? Now, we think, but Klaus Landsman, who of course know well, has been talking a lot recently about what he calls, I think, toposification, or something like that, which is like a sort of covariance way of looking at things. We think that what he is doing is equivalent to saying there's always a translation from here to here. So if you go from English into Greek, and Greek into German, or if you go from English into Greek, English into German, the claim will be there's a translation from German into Greek that will give you the same answer. And of course, there's not actually in languages. But we think this is what Klaus is saying. I may be wrong. We think this is what he's saying. It's a very interesting idea if it's true. Very nice try. Okay. So that's what it is formally. We're constructing this formal language. Okay. How does this work in quantum mechanics? Skip all this. Well, you have this. You see, what are you going to do? You're trying to construct something which in some ways meant to capture the essence of quantum theory, and it also lead you to ways beyond quantum theory, new types of construction. You've got to pick out something in quantum theory which is the most important thing to you. What's it going to be? Now, different people will choose different things. Some people will choose superposition principle. Right? Some will choose this, some will choose that. What we've chosen is the contextuality, which is implicit in the Cocker-Specker theorem, actually, is that things only have values in the context of certain things. And the idea is an very old one, going back to at least David Bohm, for example, is that in ordinary quantum mechanics, it's very well known this, that you can, if you want, assign values to things, but only if the operators commute. Now, this gets confused in the way quantum mechanics is normally taught, because you're told about simultaneously measurable quantities, you see. That's because we're so used to teaching instrumentalism, we put it in that way, but in fact, there are these various so-called modal interpretations of quantum mechanics, where you pick on a particular commutative subset, say, this has special status. That's what David Bohm did. He said, configuration space has special status. That's it, you see. And there are many such modal interpretations. So what, I flipped it again. So what Jeremy and I did was we picked on this particular one. We said, well, let us take the collection of all possible modal interpretations, all possible commuting sets of operators, all possible ways you could talk about the system without contradiction, but each one is restricted. Right? Take the whole lot together, and maybe you can capture everything. That was the idea. And we did this by constructing, we call these things contexts. If you like, they're classical snapshots of worldviews. And so we took the topos of presheaves over them. And it turns out the topos of presheaves over the collection of all commutative subalgebras of the algebra of operators on the Hilbert space is, in fact, the correct context. It works very, very well. And so we constructed successfully these key objects like sigma and so on. Now, I won't say much more about this because Chris Heinen took immediately after me will tell you, I assume, about the very interesting work they've been doing, which is quite a different way of thinking about this. And we constructed this object by hard work, you see. I mean, we worked a lot of functional analysis. It's actually quite hard work. We did it anyway. Now, they've done something quite different. What they've done is they've taken the same topos, broadly speaking, and they've looked internally at a commutative C-star algebra, worked out its spectrum in the ordinary way, internally, and get an internal locale, and lo and behold, apart from a few very minor things, if you understand, it's the same thing as sigma. This is very, very gratifying. It also turns out that some of you know the work that Chris Mulvey's been doing for about 30 years, non-commutative spectral theory. His final quantile object, we think, is the same thing. So now we've got three different ways of getting the same thing. There's the way we've done it, it's the way that Chris and Baz Spitters have done it, and there's the way that Chris Mulvey's done it. Now, it's always very gratifying, right? If you get the same thing by three different ways, you think, maybe there's something there. So I won't go into all the details, so to say we've done it. The key thing that I said that was missing, I'll just take 2 more minutes and stop, I promise, is what we call Dassinization, because if this is to work, if this thing is to be this is to replace the non-existent state space in quantum mechanics, it's this object in this topos, then the propositions about the system have to be represented in some way by subobjects. How do you do that? You have a projection operator in quantum mechanics. Now, we construct something called Dassinization. I think when the world comes to review my overall contribution to science and my death, I think they'll decide the only thing I've done that's of any significance is introduce the word Dassinization into the English language. It was done partly as a joke and partly not as a joke. I don't have time to explain it in detail, but the idea is you take a projection operator, and then the context, the sigma of V's in this spectral object, each sigma of V is the spectrum of V in the ordinary sense. So a collection of projection operators. And you approximate the projection operator as close as you can get in that set. That's the idea. Close as you can get. So you have this projection operator which is up there in this horrible non-distributive logic, you see, and you hurl it into the existential world of all the things that can be. That's why I called it, that's why Heidegger came to mind, you see. This existential act of hurling into the world. Right? You have to hyphenate things, at least hurling into the world hyphenated. It's very important. So you do that. and you get decimalisation. Anyway, it works. All these other things, the quantity value object, we might work that out, and surprisingly, it took a long time, you can actually show that each physical quantity is represented by an arrow from here to here. In other words, there is a non-commutative spectral theory. Well, as I said, that's what Moll's been looking for. That's what you get here. It is non-commutative spectral theory. The last interesting remark, perhaps, is that each state, psi, each quantum mechanical state, gives a truth object. Now, the truth object, we wrote this thing down originally in our papers with Jeremy, and also with, and it's not just, I mean, it works, but it's kind of obscure. If you go to the analogous pseudo-state, which is just the smallest object in here, it turns out just the decimalisation of this butterfly operator. It's very pretty, this, actually. You take a pure state psi, you take the projection operator onto it, you decimalise that, and that is the closest you can get to a state. So you've got this pre-sheet, so you've got all these fibres here, and you try to construct the global section, but you can't construct a Specker thing. What you can construct is this sort of wiggly thing like this, you see. Now, the astute view will notice that this letter is some obscure Gothic W, I think. And when we first discussed this, we called them Wursts. You see, why do we call them Wurst? Because you have a German sausage, the Wurst of sausage, a German sausage, you see. You try and squeeze it here, it gets bigger there. You see, if someone tells you you've got this sort of sub-object of sigma, which is the closest you can get to a point, you say, why don't you squeeze it a bit, make it smaller? See, we can do that at any stage, you can squeeze it, but if you do, it gets bigger somewhere else, just like squeezing a sausage, you see. Now, for a long time, we were calling these things to each other verse, but we decided that the community wouldn't accept that. You might accept decimalised, but verse is a step too far. If I'm wrong, please call them verse, but I think I'm probably right. So we call them pseudo-states. Okay, so that's, roughly speaking, and I'll stop at this point, is how we conceive the program, is to try to represent theories in general as physical objects, as arrows in categories between a sigma and an R. Right? And we've shown that quantum mechanics can be written exactly in that way. Nothing's lost when you do that. You can prove that always maps are injective. Nothing's lost. The whole of quantum mechanics is there, but you don't talk about probabilities anymore. They don't necessarily. Instead, you have these generalized truth values. In that sense, it's neo-realist. That's what we've done. Now, of course, it's obvious if you're going to talk about this in general, the most important thing is how do you construct. Only 2 minutes late. Thank you.
We have time for a few questions. Yes, Bruce.
How does dynamics proceed?
Sorry about your talk. That's how it goes. Oh gosh, I could say so much about that because dynamics involve time. So the question is, do you mean ordinary time, or do you mean time to seem internally? See, one thing that's clear in these quantum toposes, that space is not ordinary space. Looked at internally, space is not what you expect. There's a model for physical space internally. It's not, it's internal. Now, what about time? If you think of time as external, then the easiest way of doing this is it's like the Schrodinger picture, is that you simply have a one-parameter family of Wursts. So you've got this thing, and you put a time label on it. It's just like the Schrodinger picture. See? That's the easy way of doing it. If you ask what's the Heisenberg picture, there are answers, but it's a bit more complicated. That's the idea. But of course, the interesting question really is, what do you mean by time? Because this is external time, you see. But you can do it. It's a solvable. That's easy to say that, actually. Yeah.
As you mentioned and also emphasized, there's this very elegant thing about Topos in that they yield this nice formulation of what it means to pair a proposition with a state. Right? The state is just morphism from the terminal object into some object, which we call the state space, and the proposition is just morphism out of there, and the composition gives us an object of the truth.
That's right. Yeah, global.
So that's extremely elegant, and we could say, well, what's a state space? Well, it's a point of Topos. It's a Topos, and a P1 object. That's my state space, and then morphisms out of that are my propositions, and into that are my states. Now that's very nice and elegant. But then you discover, or you say, well, my state object is supposed to be sigma. And then you say, oh, it doesn't have any states, any global objects. And from that point on, it gets a little less elegant, at least as far as I could see. You introduce pseudo-states.
Well, I thought it was with the elegant stars, actually.
I mean, let me ask my question before you answer. So my question is, why are you so sure? I mean, sigma certainly plays an important role for something. Why are you sure that you have to identify this as the state object? Why don't you look for a state object which does have all states of a Hilbert space as.
Well, see, partly because, of course, we start off with genuine quantum mechanics. Right? I mean, this wasn't invented just out of the blue. It was something that actually appeared out of quantum theory and the spectral theory of commuting operators and so on. And it really actually do it in detail. It seems absolutely natural. I mean, it is clearly, if you have a single context, rather than the whole partially altered set of them, you just get classical physics back. So it's quite clear what you've got is contextualized classical physics. You always things build up together. And this first idea particularly, where you say, well, okay, you haven't got a point, but you've got the closest you can get, which is a thin sausage. It's like a string or a membrane, you see. So, I mean, that seems to me elegant, actually. I thought that was the elegant result. I might be wrong, I agree. But I mean, if you do it for quantum mechanics, you're driven to it. I mean, the very fact the three of us have got there by different routes is a good actual example of that. There's something special about this thing. It seems to fit. And there's a spectral theorem. We did prove with much effort that each self-adjoint operator can be represented by an arrow from sigma to this r. I mean, you know.
Right, but not the other way around. Is that true? Not every such arrow comes from a self-adjoint operator.
We think not, yes.
So someone wants to really characterize the things uniquely.
Oh, yeah, I agree. No, there's lots of work to be done. I mean, it's not a finished.
What would you do if I found, I don't know if it's possible, but if I handed you a topos with an object in it such that Homs from the terminal object into it would be precisely equivalent to a Hilbert space? You know what I mean? Wouldn't that be a good candidate for a state object?
Well, I can do that. I can take the set of all Hilbert spaces. And don't you count that?
No, a state in the Hilbert space. He means a wave function.
Oh, I see. Yeah. Well, if you
Such that Hom terminal.
if you do that, it'll be good for you. I mean, right, I don't know.
I guess we should now move on with.
No, I mean, this is a discussion meeting, right? It's not a.
So we thank Chris again. And
Okay.
Free you from this.